Welcome to Mechanical Classroom. In today's class, we are going to discuss the fourth part of Module 5. Our today's topic is mechanical vibration. Vibration occurs when a system is displaced from its mean position. System tends to retain its equilibrium position or mean position due to action of restoring force. This restoring force may be of different types. It is elastic force in the case of mass attached to the end of a spring, and it is a gravitational force in the case of simple pendulum. Now let's see the classification of vibration. Classification can be based on different bases. The first category of vibration based on exciting force is free vibration. In free vibration, no external force acts on the body and the vibration is maintained by the internal elastic forces. This vibration is otherwise known as natural vibration. Some of the examples are vibration in string, motion of pendulum. And the second category is forced vibration. Forced vibration is that vibration which is caused due to some external influences. Example for forced vibrations are vibration in rotating engines. Second category of vibration is based on a direction of motion. In this, first type is longitudinal vibration. In longitudinal vibration, particles of bar or disc move parallel to the axis of the shaft. This is the axis of shaft. This is axis of shaft, and here we can see the particle of bar or disc is moving parallel to the axis of shaft. And the second category or second type is transverse vibration. In transverse vibration, the particle of the bar or disc move approximately perpendicular to the axis of shaft on either side. And the third category is torsional vibration. In torsional vibration, particles of the bar or disc get alternately twisted and untwisted on account of vibratory motion of suspended body. So this is the figure which represents torsional vibration. Now let's see the difference between periodic and oscillatory motion. In periodic motion, the motion is repeated itself at a regular interval of time. Example for periodic motions are motion of pendulum, motion of planets around sun. Whereas oscillatory motion, in oscillatory motion, body is moving back and forth repeatedly about a mean position. Example for oscillatory motion are motion of the pendulum, vibration of the string. An oscillatory motion is always periodic. A periodic motion may or may not be oscillatory. For example, the motion of planets around the sun is always periodic, but it is not oscillatory. Motion of pendulum of a clock is periodic as well as oscillatory. Now let's see some general terms in vibratory motion. First one is time period. The time interval after which the motion is repeated itself. It is usually expressed in seconds. This time period we can otherwise define like this. It is the time required to complete one cycle. So what is cycle? Cycle is the motion completed during one time period. Frequency. Frequency is the number of cycles executed in 1 second. It is usually expressed in hertz. 1 hertz is equal to 1 cycle per second. We can represent frequency in terms of time period like this: F equal to 1 by T. What is amplitude? Amplitude is the maximum displacement from the mean position. So this is the amplitude and this is period. Now let's see another term associated with the spring, that is stiffness. Stiffness of the spring. When a spring is compressed, it opposes the applied force. This opposing force is proportional to the displacement of spring, that is we can represent spring force Fs is proportional to displacement h. So we can write equation like this: Fs equal to Kh, where K is the constant of proportionality. Okay, we call this constant of proportionality as spring stiffness or constant of spring. So we can represent expression for stiffness as K equal to Fs by H. Unit of stiffness is Newton per meter. Now let's see a spring mass model. Consider a spring of stiffness K. When a body of mass M is attached to one end with the other end fixed, the spring will elongate, which you can see in this diagram. Here this is the fixed end. Here a mass M is attached. Due to this mass M, elongation will take place in the spring, which we represent by delta. Delta is otherwise known as static deflection of the spring. In the equilibrium position, net force on the body is 0. Okay, consider the case of this spring. Here the net force in the vertical direction is equal to 0, that is sigma Fi equal to 0. So we can represent the equilibrium equation as mg minus k delta equal to 0, where mg is the downward force, which is weight, and k delta is the spring force, which is opposite to the direction of displacement. So we will be getting a very important relation: mg will be equal to k delta. This equation will be using for solving some problems. Now let's determine the expression for natural frequency of a longitudinal vibration. Consider the position of a body when it is at a distance h below the equilibrium position. The body is in motion, and hence net force is equal to mass times acceleration. This is nothing but D'Alembert's principle. We know by D'Alembert's principle, net force in the direction of motion is equal to mass into acceleration. We are applying the same principle here: mg minus k into h plus delta, where h is displacement, and delta is static deflection, which will be equal to m into a. Okay, so this is opposing force against the direction of motion. Mg is the weight, which is equal to mass into acceleration. We know mg equal to k delta from previous slide. We have arrived at a relation between mg and k delta, which is equal. So we can cancel these two terms, mg minus k delta. We will be getting minus kh equal to m into d square h by dt square. So we will be getting an equation of motion for a vibratory motion. Thus this is the equation of motion. We can write d square h by dt square equal to minus k by m into h. Comparing this equation with equation of motion, of SHM, simple harmonic motion, which we will discuss in next video. Anyway, this is the equation of simple harmonic motion: d square h by dt square equal to minus omega square h. We are comparing these two relations. Here we can see that omega square is equal to k by m. So omega square equal to k by m, omega equal to root k by m. Since the system vibrates freely, this frequency is called a natural frequency. Omega n, we can write omega n equal to root k by m. Also we know omega equal to angular velocity, omega equal to 2 pi f, that is frequency f equal to omega by 2 pi. So natural frequency Fn equal to omega by 2 pi. Substituting the value, we will be getting Fn equal to 1 by 2 pi into root k by m. This is the expression for the natural frequency of undamped free linear vibration. Now let's consider the case of combination of springs. Let the stiffness of springs be K1, K2, K3. If we replace the 3 spring by single spring, we call the stiffness of that single spring as equivalent spring. Equivalent spring is represented by Ke or simply K. Now let's consider series system. Consider 3 springs arranged in series as you can see in this diagram, 3 springs are connected in series and each spring have stiffness K1, K2, K3. Let delta 1, delta 2, delta 3 be the corresponding elongation, and here Ke is the equivalent spring stiffness. For the single spring to be equivalent to the 3 springs in series, the required condition is this is the condition. The equivalent elongation will be equal to sum of the elongation of individual springs, that is delta 1 plus delta 2 plus delta 3. We know this relation mg equal to k delta. Delta will be equal to mg by k. Substituting in this relation, we can represent mg by k equal to mg by k1 plus mg by k2 plus mg by k3. Mg is common on either side, so we will be getting 1 by ke, that is expression for equivalent stiffness, equal to 1 by k1 plus 1 by k2 plus 1 by k3 when the spring is connected in series. Now consider the parallel system. Here springs are connected in parallel. Let delta E be the equivalent static deflection or equivalent elongation. For this single spring to be equivalent to the 3 spring in parallel, the required condition is this. This is the required condition. Also we know this expression. So we will be getting this relation, that is Ke equal to equivalent stiffness equal to K1 plus K2 plus K3. So this is the condition, or this is the expression for equivalent stiffness when the springs are connected in parallel. Now let's do some simple problem. A 4 kg mass hung at one end of helical spring and is set vibrating vertically. The mass makes 2 vibrations per second. Determine the stiffness of the spring. First we can write the given data. M equal to 4 kg, F equal to 2 vibration per second. This hertz is nothing but vibration per second. Okay, so 2 vibration per second equal to 2 hertz. We have to determine stiffness of the spring K. We know the expression of time period T equal to 1 by F. Since here F is given, we can determine time period as 0.5 seconds. We also know another expression for time period, that is T equal to 2 pi into root mk. So we have determined here T value. T is 0.5. Substituting the value, mass is also given. We will be getting spring stiffness as 631.6 Newton per meter. Now second problem, a mass supported by a spring has a static deflection of 0.5 mm. Determine its natural frequency of oscillation. Write down the given data in SI unit. Delta equal to deflection delta equal to 0.5 mm. We are converting this into SI unit meter. We have to determine natural frequency F. We know mg equal to k delta. So we will be getting k by m equal to g by delta. Natural frequency is expressed by this relation 1 by 2 pi root k by m, but here k by m equal to g by delta. So we can represent natural frequency in terms of g and delta by this relation. Substituting the given value, we will be getting 22.3 Hz as natural frequency. Now another problem, a body of mass 3 kg suspended from a vertically mounted spring deflects it by 12 mm. Determine the number of oscillations of the body. Also determine the maximum force in the spring which when it is displaced through a distance of 25 mm from its rest position and then released. First of all, write given data. Here mass is given as 3 kg, delta as 0.012 meter in SI unit, H is displacement H is 0.25 meter. What we have to determine is number of oscillation, maximum force. Number of oscillation of the body is nothing but frequency. Okay, so frequency equal to 1 by 2 pi root k by m, which is same as 1 by 2 pi root g by delta in terms of g and delta. Substituting the value, these values are given. Delta is given here as 0.12 meter. We will be getting natural frequency or number of oscillation of body as 4.55 Hz. Now maximum force in the spring. We know angular velocity of the body as omega equal to root g delta. So omega equal to 28.6 radian per second. Maximum acceleration x equal to omega square into x, that is this x is displacement. Substituting the value, will be getting this 20.4 meter per second square as maximum acceleration. So maximum inertia force will be mass into acceleration, will be getting maximum inertia force as 61.2 Newton. Maximum force in the spring occurs when the mass is at lowest position. In this position, the force in the spring is equal to sum of weight of the body and the inertia force. So we have to add weight of the body to the inertia force. Adding the weight, we will be getting this is mass 3 into acceleration due to gravity. This is weight. We will be getting maximum force in the spring as 90.6 Newton. Now this is the last problem. A block of mass 50 kg supported by two springs connected in series hangs from the ceiling. It can move between smooth vertical girds. The spring constants are 4 kN per meter and 6 kN meter, as you can see in this figure A. The block is pulled 40 mm down from its position of equilibrium and then released. Determine, first one, period of vibration. Determine period of vibration, maximum velocity and acceleration of the block for this case series. Then we have to determine the values for parallel case also. Okay, same quantities we need to determine for the parallel connection. Okay, so these values are given. Stiffness of spring K1 is 4 kN per meter. So in Newton per meter we have to multiply by into 10⁻⁵. Okay, mass is given, displacement is given. Write everything in SI unit. We have to determine period of vibration, maximum velocity, acceleration of the block in both series and parallel cases. So let's consider first series case. Spring constant of equivalent spring for a series connection is 1 by K equal to 1 by K1 plus 1 by K2. So equivalent spring constant or spring stiffness will be equal to 2.4 kN per meter. Deflection of the spring is mg equal to K delta. We know this relation. This is a very familiar relation. Delta equal to mg by K. We will be getting deflection as this. Now let's determine period of vibration. We know period equal to 2 pi root delta by g. Substituting the value, we will be getting period as 0.91 seconds. Angular velocity of the block is 2 pi by t, that is 6.9 radian per second. Maximum velocity is omega into r, where r is the displacement. We will be getting maximum velocity as 0.276 meter per second. Maximum acceleration is omega square into r. Substituting the value, we will be getting maximum acceleration as 1.9 meter per second square. Now let's consider the case when the spring is connected in parallel. This is the expression for equivalent stiffness. Equivalent stiffness will be 10 kN per meter. Maximum acceleration is 8.16 meter per second square. Hope you understood the concept of spring. Thanks for watching. Subscribe and share my channel Mechanical Classroom. Also you can join my Telegram channel where you can raise your queries